And so, yeah, we're gonna start a new chapter. This topic is not on any of the assignments, but you still need to know it for the exam. I guess since it's not on any assignments, it might be a little bit more, a little bit higher represented on the exam than the other topics, but I mean, not by very much, but yeah. Yes, we're gonna look at this kind of mysterious notion of entropy and look at some cool applications of it. This actually, so entropy was introduced by Claude Shannon. Well, I don't know when it was, a long time ago, but when he introduced it, he couldn't come up with a name. So there's this famous story that he asked von Neumann what the name should be, and he said you should call it entropy for two reasons. The first reason was that the formula for entropy was already something that they used in physics, and they already called it entropy, so in some sense it already had a name. But the second reason was that nobody knows what entropy is anyway, so if you call it entropy, no one can like call you on it. They can't say you're wrong because it's just a word that nobody understands. So anyway, but now we're going to try to kind of understand it. So this notion of entropy, so we're going to kind of just start by intuitively kind of talking about what it is, and then I'll give you the formal definition. So you should think of, entropy kind of conveys like the amount of information that you're communicating, where information is measured in bits. So, so suppose I sample a random, or let's say we flip a coin, right? So flip a coin. Okay. Or let's say I flip a coin secretly, right? And I don't tell you the outcome. And then I reveal to you the outcome. It's either heads or tails, right? You should think of that as I've now revealed one bit of information. Because there are two outcomes, heads or tails. So one bit means, like a 0 or a 1, right? So revealing the outcome basically communicates or conveys one bit of information. Okay. So the entropy of a coin flip is going to be 1. Okay. There are two outcomes, heads or tails, or you can think of it as 0 or 1. And by revealing the outcome of a coin flip, that reveals one bit of information. Is that all right? Or so bit, right? I just mean like a bit is like a thing with two possible values, right? 0 or 1. Similarly, let's say I do, three fair coin flips. And let's say I let, so to be clear, like I tell you like, well, so you could get HHH, you could get HHT, right, etc. There's 8 different outcomes. And if all of them are equally likely, which they should be, if I take 3, independent coin flips, then this is like 3 bits of information. So like the entropy would be 3. Now, so this is like just trying to build up some intuition that this is what entropy is. But of course, not every, so if I do like some kind of random experiment, not every kind of random experiment just boils down to coin flips, right? Like, so it may not be so obvious how many bits of information it conveys. So like, here's another example. Suppose I put 8 names in a hat. So maybe 8 of you, I put your names in a hat. I pick one out at random. Okay. So we should think of this as like it's kind of like a random experiment, right? And if when I read the outcome, that will convey a certain amount of information. Any guesses at like, what should the entropy be of this?
Also 3.
Yeah,
So 8 outcomes.
yeah, like effectively, there's not really a difference in this random experiment compared to that one. In some sense, here we had 8 possible outcomes, all of them were equally likely. Like, in this case, okay, you can literally look at it and think of it as 3 bits of information. This, like the name that comes out of the hat may have 7 characters in it, right? But I don't care about what the actual object is that I'm picking, but it's really about the actual experiment itself. So the entropy is going to be 3, because you could, for example, take each of these 8 names, encode them by a binary string of length 3, and then pick that string of length 3, and that's the same thing as picking one of these 8 names, right? So generally speaking, let's say I've got, so if you do a random experiment, with 2 to the n outcomes, all of which are equally likely, then the entropy is going to be n. Okay. So this is talking about exactly that many possible outcomes. Okay. And the reason is, again, I could have taken all those outcomes, encoded them by binary strings of length n, and then really this is just like revealing the outcome of n different coin flips. Yeah.
And the entropy would be n only if you're like pulling a single entity out.
Yeah, exactly. So yeah, I've got you should think of it as, yeah, you can pull out one single thing, but basically whatever. I mean, well, I guess in some sense I was taking 2 things, but if there's exactly that many outcomes, I do the experiment once, then yeah, entropy is going to be n. Yeah. Okay, this is still not an actual definition of anything. So let's properly give the definition now. So first I think we maybe mentioned this definition before, but I want to talk about the range of a random variable. So for a discrete random variable, discrete just means like it has at most countably many outcomes. I don't want to do integrals and stuff. So just think of that, yeah, finitely many outcomes or maybe countably many, but it doesn't really matter. So for a discrete random variable x, let's say the range of x, which I'll write Rng of x, is the set of all little x, such that the probability that big X equals little x is positive. So this is like the range. This is just speaking about like what things are actually possible. So now the entropy. So again, it's a discrete random variable. The entropy of X is, so I'll write it as like H of X. And it's the sum over all little x in the range of big X. And then I take the probability that big X equals little x times the log base 2 of 1 over the probability that big X equals little x. So let's verify that all the things we've been saying so far are actually true for this notion of entropy. Well, so let's basically verify that this sentence is correct. So imagine I've got, so if X has 2 to the n equally likely outcomes, then we can just directly compute this, right? So the number of things in the range would be 2 to the n. So I'm just gonna, the sum is just like, you know, every term is the same. And there's 2 to the n terms. If all of these outcomes are equally likely, then every outcome has probability 1 over 2 to the n. And then I've got log base 2 of 1 over 2 to the n. These things cancel. I've just got log base 2 of 2 to the n, which is just n. Yeah, this first 2 to the n here was for the sum, right? Then each term of the sum is just this and that. And it comes out to n, right? And I really want to think of these things as thinking about like information revealed, right? If you've got 2 to the n equally likely outcomes, you can think of that as when I reveal the outcome, it's like revealing a binary string of length n, right? Okay. But more generally, so this was only talking about 2 to the n equally likely outcomes. Like more generally, like what if the number of outcomes is just not a power of 2? Like, so if the range is finite, you can just do the same calculation and you get that the entropy is log base 2 of the cardinality of the range. So in some sense, if there's like an experiment with 3 possible outcomes that are all equally likely. Oh, yes. So if the range is finite and so if this requires all outcomes to be equally likely, right? So if all, so like if the probability, this is assuming the probability x equals x is 1 over the size of the range. For all x. In the range. Yeah, everybody, that's. So it's kind of like, okay, now it becomes a bit weird because before we were talking about like an integer number of bits that we're revealing. Now, let's say I have 3 outcomes and all are equally likely. I would say that this is like revealing log base 2 of 3 bits of information. It's kind of a fractional number of bits, but yeah. I think today we're not going to really see any applications of entropy, but we'll see that tomorrow and Friday and next week as well. But for today, let's just kind of build up some properties of this this notion. So the first thing I want to say is that so for any random variable, x with finite range, so the entropy of x is always at most log base 2 of size of the range of x with equality if and only if everything in the range is equally likely as an outcome. So the probability x equals x is 1 over the size of the range of x for all little x in the range of x. In other words, equality. So this is just rephrasing this in a like kind of a smoother way. So it's equality if and only if x is uniform on its range. In other words, like if I know, like, let's say my range has size 100, right? So this will give me a bound on the entropy. And it's saying if I want to maximize the entropy with a range of size 100, then you should take a uniformly random variable on that range, right? Which kind of makes us, if we're talking about conveying information, maybe that makes sense. Like suppose I have some random variable where it's equal to, or like, let's say the range is just 2, right? So we had a coin flip that reveals 1 bit of information, right? Now imagine I've got a very biased coin flip where 99% of the time it's heads and only 1% of the time it's tails. And now I say, okay, I tell you that distribution, I say I'm going to go to a room and flip the coin. I'm going to tell you the outcome. Like, how much information am I really revealing? 99% of the time, like, what the outcome is going to be. I mean, it could be a tails and then you get a big surprise, but most of the time I'm just going to tell you it's a heads, right? So in some sense, that random variable conveys less information because the outcome is more predictable. So this is kind of saying, yeah, if you fix the size of the range, the most informative the highest kind of amount of information revealed is gonna be from the uniform distribution, because that's the least predictable one. Okay, so this comes down to just some convexity stuff. I'll maybe just kind of sketch the proof and move on to something else, but here's the proof idea. So let me rewrite the entropy slightly. So I'll just write it again. So it's probability x equals little x. Times log base 2 of 1 over that probability, which if you use kind of logarithm rules, you can say this is like this probability to the power -1. So you can kind of pull the -1 out. This is negative sum over all x in the range. Probability x equals x. Log of probability x equals x. So the only difference, like I just took this -1 exponent and brought it over here. So the function, if I take the function f from 0 to infinity to reals, defined by f of x is x log x. Oh, there's a subtle thing about whether the base of the logarithm matters or not, but the base of the logarithm doesn't really matter because it's just convenient though when you think about information in bits to deal with log base 2. But I may at some point just forget to write the base because of the change of base formula for logarithms, you could just change the base and it's just multiplied by a constant factor. It doesn't really change anything, but anyway, so I think this function, it's convex. You can kind of see that because, well, one way you can see that is take the second derivative and show it's always non-negative. Oh, it's not just convex, but it's strictly convex. So yeah, the second derivative is positive. Or you could think of this as like f of x. You can kind of think of it like, if I ignore the log, that's like a linear function, right? It's just f of x equals x. And then the log kind of bends it up like it's linear times something, right? So it's gonna grow like a bit faster than f of x equals x. It's convex. By Jensen's inequality then, so like well, so now just apply, so like the relevance of this is that this function is sitting inside of here. So to finish the proof, just apply Jensen's inequality. That tells you, if I take away the minus sign here, that tells you how to minimize this sum. is by taking all the probabilities to be the same. If I've got a minus here, that's now talk about maximizing the sum, is again by making all the probabilities the same. So. Well, it's kind of a proof, but some details left out there. But all the details are in the notes. Oh, yeah, so that's kind of like proving the upper bound, and then to characterize equality, we use the fact that this is strictly convex. So that the strictly word is like important for saying it's equality if and only if it's the uniform distribution. Okay. So the next idea I want to tell you about is that information. So remember, entropy is like a measure of information. So information, or in other words, entropy is kind of additive. But you need to be careful about dependencies. What do I mean by this? What I mean is like, if I do an experiment, suppose I flip a coin, right? That revealed one bit of information. So that has entropy 1. And if I flip another coin, and I ask about the kind of joint entropy of the two random variables, well, each of them had entropy 1 plus 1, entropy 2, right? So so basically what I want to say is like, if X and Y are independent, then the entropy of the pair XY, by which, what I mean by this is like, well, for example, for coin flips, right? X is the first coin flip, Y is the second, and XY is like the pair together, right? It's like either heads, tails, right? Then, then you can just add up the entropy. But like, one way to think about this, like suppose I give you the information, or yeah, let's think about why dependencies are, we have to be careful about them. So suppose I give you the information, squirrels are mammals, right? Maybe you didn't know that before, and I've revealed that information to you. You've learned something, right? Now I tell you that owls are birds. So now that seems like that adds up, right? Like I've learned squirrels are mammals. Those are kind of like separate things, bits of information. I've learned two things, and you can kind of add up what you learned, right? What if I now tell you squirrels are mammals, but then the second bit of information I tell you is squirrels are animals. Actually, once you've know that they're mammals, I've actually told you nothing in the second sentence, right? So and it's because like there's too much dependency between these two bits of information. One kind of implies the other, right? Let's look at an example with no squirrels in it. So the X be like a pair of random variables, X1, X2. Where X1, X2, each of them is just is a coin flip, independent of each other, so. So it's either like heads, 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 tails, tails, heads, or tails, tails. And let Y be a random variable. Where I set it to be. Zero if X1 equals X2. Meaning it's zero if they're both heads or both tails. And let's do a slightly weird thing that. Otherwise, I just output the actual outcome of X, so. So the entropy of X is kind of. By what we've been talking about, is definitely 2, right? Let's look at the entropy of Y. Will it clear the definition of Y? Either outputs a 0, or it actually outputs whatever X was. So this has 3 possible outcomes, right? Like Y is gonna be 0, like with probability 1/2. It's gonna be heads, tails with probability 1/4. Or it's gonna be tails, heads with probability 1/4. Okay, so it's not hard to compute this. Just from the formula. It's a half log base 2 of 2 plus 1/4 log base 2 of 4 plus 1/4 log base 2 of 4. Which I think gives you 3/2. Log base 2 of 4 is 2, log base 2 of 2 is 1. It's like that. So imagine imagine I'm going to reveal X and Y to you. Right? Let's say we sample this, right? We flip 2 coins. Suppose I do it in this order. I first tell you the outcome of X. Okay. You've now learned 2 bits of information, right? And now I tell you the outcome of Y. Have you learned anything? Right, because Y is totally determined based on X, right? So, yeah, so basically, I mean, the entropy of X and Y together should be 2. Right, because if I tell you the outcome of X and Y, okay, we were thinking about it in a certain order, right? I tell you X and then I tell you Y. If I know both of those things, I just really all the information I know is already encapsulated in X. If I tell you both of these things, I've really just told you X, right? Y is irrelevant. But now, if we think about that in the other direction, suppose I tell you Y. So I've kind of revealed 1.5 bits of information, right? And I want to kind of have some sort of notion to say that like, if I tell you Y first, okay, the thing is, if I tell you Y first, in this case, if X1 is not equal to X2, you actually know X now. But in this case, which happens kind of half of the time, you don't actually know X yet. What I want to say is that you know, so I want to kind of develop this kind of idea of conditional entropy. So let's say the conditional entropy of, let's say, X given Y. So here now I'm talking about two general random variables, X and Y, is the amount of additional information that you learn or you obtain by learning the outcome of X after knowing Y. We take this as H of X given Y with like a vertical bar like this. I guess what I'm trying to say is in this specific example, if I learn X after Y, or sorry, other way around, if I learn the outcome of Y after knowing the outcome of X, that should be 0 in this specific example, right? However, in the other direction, does anyone have like a guess? I mean, I haven't defined this properly, so there's no way for you to compute it, but
Should be like a half, like half of the time you're getting one bit and half the time you're getting nothing.
yeah, it turns out to be a half. There's various ways at this point to like kind of try to justify this. One way is the way that you're saying. Another way is just like, if you think about it, if I reveal Y, I get 1.5 bits of information. When they've both been revealed, I've got 2 bits of information. So how much more do I get by learning X? It's like whatever is left over, right? To go from 1.5 to 2, revealing X should give me an extra half a bit of information. So this is what I mean about information is kind of additive, but you have to be careful about these dependencies. So this kind of brings me to this important thing called yeah, okay, I guess I need to define conditional entropy properly. I almost don't want to. I'm going to define it properly, but let me tell you about the punchline, like what's important about this definition, and then I'll tell you the definition. In some sense, if you never knew, you don't even know the definition of conditional entropy, but all you know is this chain rule for entropy. Like, if all you know about conditional entropy is this, that would be good enough. But I will give you the proper definition. But the chain rule says that if I have a sequence of random variables, x1 up to xn, and I take their entropy. So you should kind of think of like, here we had 2 random variables, x and y. And we computed their entropy. But this is just more general, right? x1 up to xn. That's the same thing as the entropy of x1. Okay, meaning, so this is how much information I gain by learning the outcome of x1. plus. Now I want to say the amount of additional information I get from x2 after knowing x1, which is entropy of x2 given x1. So this conditional entropy thing. But then now imagine I reveal x3 and I already know x1 and x2. So the next thing should be h of x3 given x1 and x2. So on up to the entropy of xn given everything I've seen before. So like I said, I haven't actually defined what this thing is, but this is what's important about it. Right. And this makes intuitive sense that if I tell you n different facts, the amount you learn is the amount you learned from the first fact, plus the second one, given what you already knew about the first, right? Because there might be overlapping information there. Plus the amount I learned from the third thing, given that I already know the first two, and so on and so forth. Okay, so let's actually properly define conditional entropy. Two random variables. X and Y. And some little y in the range of y. Define the entropy of x given that y equals y by as follows. So it's h of x given y equals y. This is not quite the thing we want to define yet, but I have to define this first to get the other one, to get the thing we really want. So this is the sum overall little x in the range of, I would like to say it's in the range of x, but technically it's like the range of x given that y equals y. So what I mean by this is the set of all x such that the probability big X equals little x given that y equals y is positive. It's all the possible values for x given that I know that y equals y. Then you take the probability x equals x given y equals y, log base 2 of 1 over that probability. It's pretty much the same definition as entropy itself, right? You can think of this as like the amount, like for each little y in the range of y, this tells me how much information I would get from x if I knew that y was equal to that particular value. That might be kind of implicitly what you were computing in that example, and then you were averaging that out over all the possibilities, and that's exactly what we're going to do. So we now want to take this quantity for each little y and just average it out over all the possible outcomes of y. So the conditional entropy of x given y is the sum over all little y in the range of y. Probability that y equals little y times the entropy of x given that y equals little y. You can just think of this as like kind of smoothing out over all the possible outcomes of y, right? Like this quantity here tells me if I know that y is equal to this specific value, this tells me how much information I get. And I just average that out over all the possible values that y can take. Oh, and the notation is h of x bar straight line and then y. And this chain rule thing, it follows from the definition of the conditional entropy. Just by, I don't know, properly using how logarithms work and stuff like that. Like this formula, it does just kind of come out of that. You wanted to like it's maybe instructed to just even think of two random variables and see how that works. But yeah, so for example, like h of x, y is h of x plus h of y given x, for example, right? It's not too hard to prove that.
What is the actual definition of h of x and y?
Yeah, so this is like, so the actual definition of this is, I mean, the thing is like, all of these random variables we're dealing with, they're just, you do a random experiment, you get some kind of outcome, right? That outcome, I mean, for example, it could be a head or a tails. Or it could be a string of 17 heads and tails. In some sense, that's like, I guess if I just let z be the random variable x, y, meaning sample x and y, and then like look at what that is as an ordered pair, then h of x, y is h of z. So yeah, random variables, they just have an outcome which is some mathematical object, and then yeah. So if you want to like write what this is, go through all the things in the range of x and y, like the things that the pair x, y can be. Take the probability of that, log of 1 over the probability of that. One little quick thing I just wanted to mention. Another thing that's intuitively clear. So if I take any random variables, let's say x, y, and z. Actually, maybe I'll just write these quantities and I'll say there's going to be an inequality here. Oh, sorry, this should be given. So this is like the conditional x conditional on like the entropy of this given at y and z versus the entropy of x given z. Sorry, just y. Which way do you think it goes? Think of this as I've already told you the outcome of y and z, and now I'm asking how much more information do I get by learning x? This one I've only told you y, I haven't told you z, and And this is like how much information do you get by learning X? Which one should be bigger, left-hand side or right-hand side?
You're right.
Yeah, right? Because like, I mean, in fact, I could have, I gave you the information of Z, I could have kind of slipped and given, I mean, maybe that completely gives you the information of X itself, right? So indeed, yeah, it goes this way. And you can prove that just using the formulas and like, I think Jensen's inequality, it's not hard to prove, but so it fits with the intuition, right? I've told you less so far, then the amount of information you're gonna get by learning X is can only be bigger. But I've told you less, right? Okay, so I'll see you guys tomorrow.